So yes, I've been asked to give a bit of feedback from how we are using PyHF in SModelS, PyHF and associated products that come with it. So this is basically a talk for the SModelS collaboration, and from the I just want to point out that from the people listed here as collaboration members, Gael Alguero was a former PhD student here in Grenoble, and he was the person who actually developed the first interface to PyHF, which really was a major step forward for us. And Sahana and Timothy, current PhD students, Sahana in Vienna and Timothy here in Grenoble, and they provided all the plots that I'm going to show. So thanks to them. Okay, for those people who are not familiar with SModelS, just a very brief, in a nutshell, SModelS is a public tool for the fast interpretation of LHC searches on the basis of simplified model results. So what we are reusing are really the cross-section upper limits and acceptance times efficiency values that have been developed from SUSY and exotic searches in the context of simplified models. The working principle is illustrated here in the scheme on the right. So if you have an input model, it can be an SLHA file with masses, branching ratios, cross sections, or an event file. The SModelS decomposes this into simplified model. The full scenario, the full BSM scenario, decomposes it into simplified model components, which are then compared to the constraints that exist in a large database of experimental results. And this process is fully automated. The results that we have in the database, they come mostly like to 90–95% from SUSY searches, but the tool itself and the whole working principle is applicable to any BSM model with a set tool-like symmetry, such that you have a pair production of new particles and some missing energy in the end, or long-lived particles in the end. And the kinematic distributions are not too different from those which were assumed in the original experimental analysis. So these are the constraints. Good. The big advantage of SModelS is speed. So it's simple to use, and it's very fast because there's no Monte Carlo simulation involved. And we have a very large database of experimental results. Also, we can treat Atlas and CMS, run 1 and run 2, prompt and long-lived researches all simultaneously in one run. We also have an easy classification of unconstrained cross sections. But the limitation is, of course, the kind and variety of the available simplified model results, which are mostly provided by either Atlas or CMS. Just as an aside, actually, the first SModelS paper came out like 10 years ago, so anniversary is next week. It's kind of a nice anniversary talk. Now, the experimental results we're using in SModelS are either upper limit maps in terms of simplified model parameters, or acceptance times efficiency maps. So this is what we generally colloquially call efficiency maps. And it's these latter ones that allow us to compute the number of signal events expected in each signal region of an analysis, and from which we can then compute the likelihood. So this is, once we found these efficiencies, this is basically like in Aki's talk this morning, when they do the recasting with checkmate, they compute the acceptance times efficiency values for the new signal. We directly use these kind of maps to determine the signal counts in each signal region. And then from then on, the computation of the likelihood is equivalent. And this is, of course, where PyHF comes in, because if information on signal region correlations is available, the signal regions can be combined, and we can do a much more sophisticated statistical evaluation. Now, the interface to PyHF from SModelS was already established in 2020, so I think we've been the first users of PyHF, external users from the Fino community. And really, whenever a statistical model is available, it's in JSON format, we try to use it, or we use it. It's a real boon for us. Now, since SModelS needs to be very fast, we typically use simplified JSON files. So simplified meaning they've been digested with this simplify tool from Eric Jarnett. But of course, we then test very well to a great extent that this is actually a good approximation. And the usage of the full likelihoods instead of the simplified ones can be enforced now. So this is new since version 2.3 of SModelS. It can be enforced through database add-ons. So typically one specifies the path to the database or to the database pickle file in this way here. The path can be latest, which means that SModelS will download the latest database pickle file. And then if you specify plus full likelihoods, all the simplified JSON files will be replaced by the full ones in the database. Okay. Now, just a brief word on what is actually in the database. So in total, we have experimental results from 111 Atlas and CMS publications. Some from run 1, from run 2, we have 38 Atlas results, and 7 of them are 38 Atlas analyses, and 7 of them are with likelihoods to be run with PyHF. And there what we use are the background only JSON files. So you have these 7 analyses highlighted here in yellow. These are the ones we use. There is one analysis that we have in the database. I think this is this Atlas SUSY 1822 multi-jets states, which has full likelihoods available on HEP data, but this is like one background only file for each signal region, so separately. And that's of little use to us, because what's relevant for us is combining signal regions. If anyway, we use only the counting in whatever is the best signal region, then it's not too useful. Okay, so that's the status in the database. Now, let's have a short look of how useful this really is. All this information about the full likelihoods. So what we do is usually we compare best signal limits from best signal region versus full likelihoods versus simplified likelihoods in the database validation. So here is one example from Atlas SUSY 2018-05. So this is the search for phenomena both in hadronic and now in strong and electrolytic production in events with 2 leptons, jets, and missing transverse momentum. And what I show here is the electroweak interpretation, so production of charginus neutralinus decaying into WC in the final state, plus missing energy. You have on the left the expected exclusion, on the right the observed exclusion plot, so the 95% confidence level limit. Dashed is the limit we would get when using only the best signal region. Dash dotted, well, okay, full solid line is when you use the full Hiss-Factory model with PyHF, and dash dotted the simplified one. In this case, the simplified one actually works better than the full one, which is probably related to uncertainties that we also have in the efficiencies. But this is a very good match, and so we confidently use the simplified JSON file in the database. Here, this is the Atlas 2018-32 analysis. So this is a search for charginus and leptons decaying into final states with 2 leptons. So this is targeting, for example, chargino pair production with both charginus decaying into Ws. Again, you have the validation plots, left the expected exclusion, on the right observed exclusion, and here you see that it's really essential in this case to combine the signal regions, because with using only the the most sensitive signal region here in the dotted line, it's completely off. It's completely different from the official Atlas result. Again, the simplified JSON file works very well, reproduces well the observed limit from Atlas. But what's strange is that for the expected, it does not perform so well. So there, the full statistical model is much better. Something that's peculiar about this result here is that we really need to include the control regions in the fit, otherwise the result is off. Okay. Another example is from an electroweak search in final states with one lepton in missing energy and Higgs boson. So this is Atlas SUSY 2019-08. In this case, the full statistical model here on the right-hand side plot for the observed exclusion with in the solid line allows us to reproduce well the official Atlas limit. But the simplified one gives an over-exclusion. So in this case, we really use the full JSON file, the complete spectrum model, also in the database per default. One question that we cannot really answer is why with the full JSON file we reproduce well the observed limit, but not the expected one. So the expected one is it shows an under exclusion. Okay. Now this one is an example where we do not have a statistical model, but it would be really, really relevant to get one. So this is the Atlas search for leptons and charginos decaying into 2 leptons, or in final states with 2 leptons, for scenarios with small mass splittings near the W mass. And when using only the best signal region, we basically have no sensitivity at all. So what we do in SModelS is to make a mock-up covariance matrix to those, assuming that different flavor and same flavor signal regions are uncorrelated. So we can combine them in a very naive approach. So with this, we can kind of reproduce the official Atlas limit, but to have the full model, which will really be much better. That's a plea for more information from this analysis. Okay, so I'm doing about time. Okay, so this is just using PyHF basically as a backend for computing limits on signal cross sections, determining basically an exclusion confidence level or the excluded cross section. But another use that we make from PyHF related material that's provided by Atlas is that we sometimes extract efficiency maps from the patch sets. So these patch sets that are shipped with the background only JSON files on HEP data, they allow us to extract these acceptance times efficiency values for all signal regions. So they're not always provided as the auxiliary material in the original publications. And besides, you can also extract them for the control region. So that's something that's rather useful. Now, one example where we've invested a lot of time, especially Timothy has done a lot of work on this, is the Atlas search for charginos and neutralinos in final states with boosted hadronically decaying bosons. So Atlas hadronic electric search for sure. So this analysis has 7 signal regions that target WW, WC, CC, WHiggs, C-Higgs final states. So we call them colloquially exclusive signal regions. So where exclusive is not statistically exclusive, but exclusive with respect to the gauge bosons that appear in the decay. And they also consider 3 what we call inclusive signal regions. So VV, where V can be WRC boson, VZ, and VX. And the analysis originally published efficiency maps only for these 3 inclusive signal regions, which are supposedly independent. So 4QVV, 2B, 2QVZ, and 2B, 2QVH, which are supposed to be statistically independent from each other, but that also encapsulated most of the necessary information for interpretation. Now, when we use those, some validations, they work well, but others don't. So here you have two examples. On the left, the plot of the observed exclusion for the CC plus MET final state. We're combining the counts from the 4QVV and the 2B2QVZ signal regions. Works well, and then well reproduces the atlas, the official limit. But for the WC final state, so assume Giorgino-Neutralino production, we get an over-exclusion in the same approach. So it's kind of a question of what is going on. I mean, do we lose information by using these more inclusive signal regions or whatever? So there was a lot of exchange with the atlas analyzers, which led to actually the full hist factory file being published on HEP data quite after the original release of the analysis. So this I'm very, very happy about. And thanks a lot to Xion Chen, who really invested a lot of time in making this happen. Now, this new HEP data records contains the full background-only JSON file and patch sets for a diversity of simplified models. So what we are really interested in are so on the quotes pure simplified models, so with very specific final states, like listed here. And from these, we can extract the efficiency maps for these exclusive signals. Now, for CC, Higgs, and Z-Higgs final states, we don't have pure simplified model or patch sets, but what we can use is or have to use this Higgsino, Axino sort of models, but this is much more, this is somewhat tricky. So we are still investigating whether we're doing everything correct with those. So yeah, to have patch sets for pure decay modes would be more useful for us. Anyways, these plots here, they compare the exclusion we get from the inclusive signal regions with respect to the exclusive signal regions. So here on the left for WW plus missing energy, dotted line is the inclusive signal region SR4QVV, and the full line the SR4QWW. So that's really targeting this final state, and you see there's an improvement with respect to the official atlas limit. Similar, although the effect is smaller for the W Higgs final state, but for WC final state, which basically populates two signal regions, so the 4Q and the 2B2Q, either in the VZ or in the WZ category, we get a slight over-exclusion. The over-exclusion is more pronounced with the inclusive signal regions, so we do better with the exclusive ones and combining with PyHF. But somehow, using just only the best signal region still gives a closer match with the official atlas results. So this is something where we really don't know what's going on. Okay, this in comparison the expected limit. So it's basically the inverse behavior compared to the observed one. So for the expected limit, actually the inclusive signal regions performs better. It's also a bit funny. Okay. We also do detailed validations for scenarios with mixed final states. So here's an example for hexeno production, which then decays down to an oxeno with 50% branching ratio into C bosons or Higgs. And you see it performs well. Similar for Vino production decaying into Vino. In this case, with 100% branching ratio of the neutrino 2 to Higgs. This also works well, but again, when the final state is C, so in this case it's Vino production, where we get a mix of WW and WC final states, and in this case we observe an under exclusion when we use the exclusive signal regions and the combined signal regions with the full or the simplified hysterectory model, which is a bit strange because if you remember from before, in only WC final state we had an over exclusion. WW gives less contribution and then anyway has less sensitivity. And in this case here, we observe the result is an under exclusion. So we are still investigating what's going on here. But in any case, I mean, just to have this information from the hysterectory file and the patch sets, it's really useful for us. Okay, that brings me to conclusions. So full statistical models are extremely useful. We make in SModelS, we make less sophisticated use than, for example, for the EFT fits, and then scrutinizing all the, you really need access to all the nuisance parameters. But still, in SModelS, we are also mostly using the simplified ones when for speed reason, whenever this works well. We're also thinking of machine learning, making machine learned models of the full likelihoods to really speed up our calculations a lot. Some differences with respect to the official Atlas limits, they really still need to be explained. So we are investigating. Tools for different simplification schemes would be really welcome. I mean, this is something we've been discussing since a while. So, for example, the simplified likelihood with linearized systematics proposed by Nicolas Berger would be interesting. But in any case, I mean, it's really good to always have the full background only model because one can always simplify afterwards. And last point is that patch sets for pure simplified models, they are also very useful because they allow us to extract efficiency maps. Okay, so my take on this is thanks a lot for all those developments from PyHF. I have a last slide with open issues if you're interested. So things that don't work well, but in principle, I'm done. Okay, thanks for your attention.
Thanks very much, Sabine. And also, yeah, thanks to you and the rest of the SModelS team for some long years now of collaboration with us. So we appreciate it. So yeah, maybe let's go to Zoom first, but then maybe we can talk about some of the issues and other things. Well, so Jordan is here, but he has his hand raised on Zoom, so let's go to him.
I'm just taking a
it's fine.
Here. Thanks for the talk. As usual, it's always a good talk. I think some of these we're gonna have to either take up with the analysis team, but later if we find that there's an issue with what's been put online in HEP data, I did want to ask before we get there, what you say for this last bullet point here in your parentheses about where you say that it's not possible for patch sets with mixed production / decay mode. What do you mean here?
Sorry, can you repeat the question?
So what do you mean by the parentheses in the last bullet point?
Sabine, could you hear the question?
Yes, so you mean why it's not possible to use patch sets for mixed production and decay modes? because our efficiency maps are really for simplified models. So since we decompose every full model input into simplified model components, the efficiency maps that we have in the database, they need to be for a specific simplified model topology. So if you have a patch that does like has Vino production with a part of the signal comes from Chargino pair production, giving W final state, and another part of the signal comes from Chargino Neutralino production, giving a WC final state. We cannot separate the two different contributions from in the patch sets.
Right. Okay.
So we cannot extract the efficiency maps that we need. Yeah. So this is why.
Sabine, I know you're not saying this is like an issue with the physics on some level.
But a patch set with mixed branching measures, for example, like here, this is super difficult, if not impossible, to use. For us, it's useful for other purposes, but for us in SModelS, it's difficult.
Okay, I thought by the phrase in there you were talking about, because we do have patch sets where we have different kinds of simplified models put into the same patch set. And I thought you were referring to a technical issue with being able to extract the information out of the patch set. We're talking more about the physics where the underlying signal being put in there, you cannot separate out because it's reduced before it even goes in the patch set.
Right.
Okay. I guess maybe you want to move on to like the actual technical difficulties with some of these analyses, maybe.
Yeah, so I think on slide 24, in general, thanks for raising these, although I think for your first 3 bullet points, we're probably going to need to, well, for the first bullet point, this might be something that we can look at collectively over the next day, but I think for the other ones, this will probably might need us to talk with the analysis teams. But for the backend dependence, apologies, I can't remember if we've talked about this on GitHub before or not. So if we have, I'm sorry, but it'd be interesting to kind of follow up a little bit more on like this backend dependence, because I assume here that what's really the relevant bit is the choice of like optimizer and maybe optimizer like algorithms. So because I would hope that the actual I guess like vectorized operations should be mostly interchangeable. So yeah, so if we're able to follow up, sorry, go ahead.
But in sequence, like this issue with the likelihood from 2018-06, this is a long-standing issue and never got resolved. I mean, there's a GitHub issue on that one and so on. So in the end, we gave up.
Okay, good.
Okay, but it's not just a strange behavior. For SUSE 18-16 that we can't reproduce, this is probably an issue with the efficiency maps. So this is it's just it has nothing to do with PyHF itself. The backend dependence, this is something we observe when running on a large cluster with parallelizing. So probably Wolfgang can say more. Yeah, he can probably say more about this because he looked in detail also in which optimizers are used and so on.
Are you guys hearing me?
Yeah, yes. We can hear you, Wolfgang.
Yeah, actually the biggest difference was, and we only realized a bit later, was that with PyTorch we got Hessians and with NumPy we didn't. And we use the Hessians to estimate uncertainties, right? And so now we've only been doing it in the last 10 days or so. So now we're replacing the Hessians with numerical Hessians, which actually seems to be working. That's the biggest difference. Everything else is as you would expect, right? you do expect some numerical differences if you change the backend.
Yeah, but sometimes the differences were really huge. When just using like just saying backend PyTorch or backend NumPy. In some pathological cases, the resulting the results were really different. I mean, a lot of it.
Yeah, I mean, yeah, as Wolfgang pointed out, the machine learning backends do give you access to automatic differentiation, which definitely helps. But if you are finding issues where the SciPy optimizers are giving kind of radically different like results, then that might be something to think about.
I mean,
Yeah, I mean, I can speak.
It's just something to be aware of, that this issue exists, and then maybe warn your users specifically.
Well,
Oh,
from the Atlas Susie hat on, any analysis that has published likelihood only ever gets validated with JAX and Minuit. That's how the validation is done right now. So you won't have to, it sounds like you're either using a different backend and or a different optimizer than what is getting published when we do the validation internally in Atlas. So if the issue is that a different backend is giving different results, that's something we might need to investigate. But Alex?
Yeah, I mean, I think what's probably the case here is that there are convergence issues in some places, and then these convergence issues make the results like seem weird, right? If there's a big difference between backends, even with the same minimizer, I mean, this could purely be because of convergence issues, and one of them by chance converges and the other one doesn't. So typically, all of these things come down to something in the model causing a problem, and historically, this oftentimes has been samples where the yield prediction becomes negative. So I don't know if you tried out yield clipping. That's why I'm asking, like, if you have the link to the discussion, whether we talk about this there. So there are some features that might help stabilize all of this. But ultimately, it typically comes down to convergence issues, which are typically, again, related to the way the model looks like, and then the minimizer just happens to explore some region of phase space where it gets lost in. So yeah, there's oftentimes, I think, not too much to interpret like in there, other than, okay, difference means something is unstable.
Yes, clearly.
So,
Still,
yeah,
I mean, just using the tool as a tool, usually people don't try the same calculation with different backends to test. This is just by accident that for us, it was an accident that we stumbled on the problem. So it was just flagging it, that nothing more to this.
So I think that we could probably have some more discussion on this, and I'm not sure if any of the SModelS team members are going to be available tomorrow, but I think some of this would be great to discuss there as well.